Stanford University.
Okay, picking up from Monday. Okay, so we are now well into our second topic of the second half, looking at aggression, competition, cooperation, empathy, all those guys, and we've got the drill down by now, starting with behavior all the way to the right, working our way to the left, all the way back to evolution, genetics, blah, blah. Where we left off the other day was just getting into the first box worth of what's going on in the brain. What is the neurobiology of what's occurring seconds before that aggressive act, that compassionate act, all of that, as we know already, right in the middle of the limbic system, of course. As we know already, the amygdala is playing a really central role and seeing all the evidence for it, lesion studies, stimulation studies, the bizarre, rare realm of humans who have had lesions or stimulation there, accidents or intentional psychosurgical interventions, beginning to look at the amygdala there and the role that it plays. Now, part of what becomes relevant there is seeing the kind of information that the amygdala is getting. And an important thing to focus on is something that was mentioned back in the limbic lecture, the notion we ended with the other day, the amygdala. Okay, so you look at somebody who has had amygdaloid damage and they tend to not be able to detect fear-evoking faces. They are overly trustful. They are underly skeptical. They are not taking in the sort of information we would that leads us to conclude this is a circumstance that demands arousal, vigilance, so on. One of the things that was seen, interesting study that I noted at the end the other day, was looking at people with amygdaloid lesions, Damasio and his group looking at this, keeping track of where the eyes are looking. When they see another face, they are not looking at the eyes anywhere near as much as everybody else would. They're instead tracking around all sorts of extraneous parts of the face. Normally people look at the eyes a whole lot. And what that winds up showing is not only is the amygdala playing a role in deciding this is a fear or aggression evoking stimulus, the amygdala is also on the lookout for it. And what we will see in a little while is one of the things testosterone does is make the amygdala better at looking for fear and anger evoking faces. So part of what the amygdala is doing is taking in sensory information. We touched in the limbic lecture on one interesting aspect of it. Okay, back to that business, that the limbic strategy of counting the number of synapses, that strange business about olfaction being only one synapse away from lots of parts of the limbic system, including the amygdala. If you were dealing with a rhinoencephalon, the olfactory world is being so emotional for a rodent. For us, we've got something else interesting happening. And I think I mentioned this. Okay, so you got the visual system, and what we have is the usual rule that visual information, just like auditory, just like tactile, comes in and goes by way of a way station along the way, whose name we won't worry about, and goes through all these levels of cortical processing and biocore. People will remember layer 1, doing dots to lines to moving lines, all of that, eventually processing, assessment, come up with an idea that, oh dear, this is a menacing face, and then let the amygdala know about this. What was also found a number of years ago is that there is a shortcut, there is a branch coming off of this way station called the lateral geniculate. There's a branch coming off which then is only one synapse away from the amygdala. What we heard is that's really useful in that it can get you fear-evoking, arousing information that much faster than going through all this cortical processing. It is a shortcut. It is not one synapse away, but it certainly makes for fewer synapses. That's a faster system that we've got in order to very quickly pick up information that should be of interest to the amygdala and all of its fear, anxiety, aggression type concerns. So that's wonderful. That's terrific for the amygdala. What I think we also heard is it comes with a downside, which is you send all this information through all these different steps there because it's doing all this cortical processing for you. It's figuring out all the details of the sensory information you're getting in. This way, it gets to the amygdala faster, but what gets there is less accurate. you're more likely to make a mistake. And that's the whole world of people reacting really quickly to some peripheral piece of information, which turns out to be different than they thought it was, and before they knew it, they had reacted. This is the cortex sitting there still trying to decide, is this a three-dimensional object or a two-dimensional one? And through this route, you've already stabbed the individual. This is a very, very clear trade-off: faster information, less accurate. And there's by now a lot of evidence to suggest that this particular pathway is hyperexcitable in individuals with post-traumatic stress disorder, where that whole world of all sorts of acute sensory stimuli suddenly fling the person back into where they were when that happened to them, and without the processing time to figure out, this isn't exactly the same. In fact, this is a world away from where that happened. Already, the amygdala is responding. So these shortcuts, but telling you one of the things you give up with the shortcuts is the analytical accuracy. Okay, so amygdala for that. Amygdala equals fear, equals anxiety, equals aggression. Isn't that interesting? In a world in which amygdaloids are not afraid, there's no aggression, that whole theme there. The amygdala isn't always about fear and aggression and anxiety. And it's very informative, the examples where that's not the case. One case, really interesting syndrome called Williams syndrome, which we're going to hear a lot about in the language lecture. Williams syndrome appears to be a poorly understood imprinted genetic disorder where you get, among other things, kids who are unbelievably facile with language and emotional expressivity. This whole world of Williams kids, it's this fascinating disorder where you get kids who are basically borderline retarded in terms of cognitive function, yet they have this spectacular adeptness at language, at reading emotions in other people, at communicating them. They are famously affectionate kids amid being very cognitively impaired. We'll see in the language lecture, most people think about Williams syndrome as an interesting example of the modularity of language control in the cortex. You can have very, very sort of facile language skills in these individuals who nonetheless are typically in the IQ range of about 70, argument being, we'll see in a couple of weeks, that there are specialized cortical areas for language. For our purposes, the interesting thing about Williams kids, and eventually Williams adults, is they are extremely trustful. They are extremely gregarious. They are incredibly vulnerable as adults to being taken advantage of by other people. And what you see with Williams individuals is you basically cannot evoke amygdaloid activation with scary faces. They don't register in someone with Williams. So there we see that this is not universally serving that role. Another example where there seems to be an exception until you think about it a little bit, people with social phobias. What studies have shown is, show a social phobic any sort of face, human face, and their amygdala activates. Oh, that's not telling us anything informative. It's telling us something very informative, which is if you have a severe social phobia, any face is a scary face to you. All faces do that rather than only ones communicating certain threatening emotions. Another one that seems puzzling, but which then makes perfect sense when you think about it, when you take people with clinical depression, the amygdala doesn't necessarily activate when you show them a picture of something frightening. It activates when you show them a picture of something sad. Okay, so now instead of doing fear and depression, the amygdala does sadness or something. If you think about it for a minute, that makes perfect sense. What the amygdala might very well be doing is responding to whatever it is that is most ethologically frightening to you, you as a species, you as an individual. If you are somebody who's depressed, the most frightening thing on earth is something sad around you as more justification for feeling even more depressed. The amygdala being far more subtle than, ooh, here's a scary predator with a knife coming at me, very much contextual. Okay, another thing that the amygdala is brilliant at, which we will come back to in more detail, but on a first pass is so depressing, is the amygdala is probably the part of your brain that is best at doing dichotomizing between us and them. forming categories, in-group, out-group, and responding to out-group stimuli. And we will see two things down the line, probably on Friday. Number one, it is really, really depressing how readily the amygdala forms some of these us-them dichotomies and the sort of thems that it responds to. Really depressing, but also some good news in there, remarkably subtle social manipulations that will change the sort of us-them dichotomies that the amygdala responds to. So stay tuned for that. Okay, so shifting from the amygdala, going to the incredibly interesting, important frontal cortex. And frontal cortex obviously was doing all sorts of stuff 2 lectures ago in the sex lecture, getting you to have the appropriate context for sexual behavior, getting to do the harder thing like leaping over streams and headbutting with other antlered beasts, if that's part of your mating season. Where the frontal cortex is particularly involved is this whole world of regulating appropriate behavior in the context of violence, aggression, competition, cooperation. Frontal cortex is incredibly important here. Okay, back to the limbic lecture. The limbic system is about subcortical structures underneath, things like that, and the cortex is about the cortex, and we heard in the limbic lecture, instead what was originally that heretical view by that neuroanatomist Nauta saying, actually the frontal cortex is part of the limbic system. It should be viewed as such, and over the years since, it being viewed as this is the cortical part of the limbic system. This is the cortical region that is intensely involved with limbic function, with emotional function. On an anatomical level, what we've already seen is, just as a first pass, tons of bidirectional connections, everything in the limbic system talking to the frontal cortex sending projections back all over the limbic system, so anatomically it's there. So in terms of what it's doing, the best way to describe what the frontal cortex is about is when there's a choice between doing something harder and something easier, and the harder thing is the better thing to do, it's the thing that makes you do the harder thing. And we'll see this plays out in all sorts of domains. The frontal cortex getting you to do the harder thing. First, beginning to see the way it works in terms of wiring. Okay, here we have reduced the entire world down to a simplified, there's 2 neurons that account for all the easier things you do in your life, and there's 3 neurons that account for all the harder ones. Here we have some circumstance where there's a circuit at some juncture, the easier but less desirable outcome. Behavior is this way, the harder one that way, and what you see is this has more inputs than this one. This is obviously some entire circuit of neurons, and this is highly simplified, blah, blah. But what we see is the way it's set up here is that there are more inputs into this pathway. This is what makes this neuron easier to activate than this one. There are stronger inputs into this pathway. This one has only 2 axons going to it. This one has 3. Yes, simplified. When you look at the wiring of the frontal cortex, it's sending projections all over the limbic system, all over motor areas. A characteristic of the projections is that very rarely are they very strong projections to any given target area. They're not the sort of projections where here's this limbic, this frontal cortical neuron that is now dumping all of its axon terminals into this one neuron down there. It does not exert a very strong influence over the excitation of any given neuron. Instead, what it has is a whole lot of weak but diffuse projections. What is the frontal cortex doing? It's slowly massaging the area there. It is giving biasing bits of depolarization of excitation. So what we've got here is, okay, the numbers are not quite working, but in any case, what we have here is, here's doing the right thing, that's harder, and it's a lot harder to get this neuron to do the right thing, that's harder, because there's less of an input than this pathway. What the frontal cortex tends to do is have these relatively weak inputs into all these systems where it makes it a little bit harder to just fall for this one. It gives more strength into this pathway. The frontal projections very rarely are activated modulating on their own. Yes, indeed, we have another example here of modulating if and only if this pathway is already struggling to do the right thing. The frontal cortex tends to be able to push it over the top there to pull it off. Frontal projections as very diffuse, relatively weak, but biasing towards excitation rather than causing it, that tends to be the thing that it does. Okay, what you see in terms of making sense of frontal function is, as we heard the other day also, a huge whopping projection from that nucleus accumbens. You remember ventral tegmentum, nucleus accumbens, this huge dopaminergic, dopamine releasing projection into there. And on a certain level, you want a totally useless metaphor, but on a certain level, what the dopamine projection is about is, so here you've got the frontal cortex. The frontal cortex for a living makes you do the harder thing when it's the right thing to do. Dopamine is, in a sense, the fuel for that activity. Dopamine, the expectation, the anticipation, the capacity of dopamine to generate goal-directed behaviors is heavily running through this pathway. Dopamine is the thing that's giving, in a sense, the frontal cortex the energy to just push you over the edge and to tell you, yes, go this way instead of this way. What's also intrinsic in this is lots and lots of frontal projections that are inhibitory in that realm. An awful lot of what frontal cortex is also doing is whispering to this pathway saying, you really shouldn't do that, you're going to regret it, I know it's tempting right now, don't do it, don't do it. This super ego sort of neuroanatomy there of frontal cortex, dopamine as very strongly stimulatory in there. The whole role of dopamine as driving goal-directed behavior. And that was the critical business we saw in that study, showing you let the monkey know that it's now entered one of those periods where if it lever presses, it gets the reward. Ooh, I know just how this works. Anticipation, that's great. Up goes dopamine. If you prevent the dopamine from going up, you don't get the lever pressing. Dopamine is not just about anticipation. Dopamine is about driving the behavior needed to get the reward that you are anticipating. Dopamine as goal-directed behavior. Okay, so what you begin to see in terms of how this frontal cortex does this making you do the harder thing, it's manifest in all sorts of domains. Easiest, most accessible realm is seeing what it has to do with cognition, the way in which the frontal cortex gets you to do the harder thing. What it helps you to do is organize bits of information in ways that makes it easier to make sense of. Here is, if you ever find yourself being borderline demented and somebody is giving you a test, this is one of the tests they're going to give you, so start preparing. And this is this horrifying test called the CVLT, the California Verbal Learning Task, or some such thing like that. But here's what they do. Some neuropsychologist sits you down and says, oh, I'm just going to tell you something, a list of things here. See if you could remember. Today I went to the market and I bought 1 tomato, 1 hammer, 1 box of cereal, 1 grape, and goes through a list of 16 of these, 1 every second or so, and they finish and they say, okay, do you happen to remember what I bought at the market today? Oh my God, it is so stressful. So you manage to get out like maybe 7 of them correct, and the person says, okay, that's very good, let's do that again. Today I went to the market and I bought 1 tomato, 1 hammer, 1 box of Cheerios, 1 box of strawberries, and goes through this list again and seeing each time how many of them you remember, beginning to see your memory acquisition thing as you're getting closer and closer to remembering all 16. It's not until you're maybe in the 3rd or 4th round of doing this that you begin to notice something, which is of the 16 items, 4 of them are fruits, 4 of them are hardware items, 4 of them are bread cereal things, 4 of them are who knows what, and they're scattered throughout. What the people typically start doing by the 3rd or 4th one is you begin to group them by categories. And instead of remembering back, okay, tomato, hammer, cereal, fruit, whatever, you first tell the 3 out of the 4 fruits that you remember. Then you tell the 2 out of the 4 hardware items. You're beginning to group the information. And what that is called is executive function. executive organizing strategy. It is sheer memory systems that are remembering sort of these 16 factoids. It is executive organizing that's telling you, do you notice some patterns there? Don't just remember it in sequence. Don't try to just remember it in sequence. Stop for a second and try to keep track of the categories, because that's going to be a better strategy in the long run. That's what the frontal cortex does. You get someone with frontal cortical damage, and their capacity to remember the learning curve is not all that different from anyone else, but they never start doing the grouping. They never start doing what we might think of as almost cognitive strategizing. Ooh, I see a pattern here, and I suspect if I put the effort into exploiting that pattern, it's going to make it more productive for me to try to remember things rather than just trying to do it in sequence. So the frontal cortex is good for that. Where else do you get in the cognitive realm the frontal cortex getting you to do the harder thing? Where you get all this information in the cognitive realm is when you study people with frontal damage. Either people with accidents or, very often, older individuals who have strokes there. There's a very distinctive type of dementia that takes out the frontal cortex called frontal temporal dementia, and all sorts of cognitive tests in those cases showing in the cognitive realm what happens when you're not having this going on throughout all the circuitry. One thing that would be given, okay, so you sit down this individual and you say, okay, you recognize this, don't you? Even though most of you guys don't by now, growing up in the digital era, but this is the face of a clock, and it comes with a little hand and a big hand, and they point in informative directions. So you ask the person, okay, you recognize this, of course, this is a clock face. Now, where would you draw the hands if I said the time was 11:10? 11:10, so sit for a minute and think about where we're going. Of course, it's 10 minutes after 11, and that's where the hands would go. Someone with frontal damage instead would draw the hands at 11 and 10. What are the rest of us doing? We're saying, okay, the easier thing is to just get gummed up on the number 11 and the number 10. Wait, don't do that, hold on. Remember, 10 is a coding for multiples of 5 minutes, because that's the way clocks are organized. So 10 is actually 2 of these, so it's 11, 10. 10 is a shorthand for saying 10 minutes after 2, and you put your hands in the right place. Somebody with frontal damage can't hold off, and they get pulled by the easiest interpretation of the sound 11:10. They draw the hands at 11 and 10. So this is what you would see. More examples. What the frontal cortex is good at is getting you to inhibit the easier route when it is a very well learned, very well conditioned one. Here's what you would do. Now you take the person who you think may have some frontal damage, and you say, okay, here's a task I want you to do. Starting with December, tell me the months of the year backwards. What have we all learned since way back in first grade or whatever, that this is an easy thing going forward, this is the harder thing right now. And you will see a person with frontal damage will say, okay, December, November, October, September, October, November, December. They manage to pull it off for a while, and then they just slip on the ice back into the easier way. It is, you normally have December followed by January, not by November. It takes more work to do it that way. People with frontal damage, they have this intrusion. They can't hold off the overlearned response, the more habitual response. You would then see, with frontal damage, something that's termed intrusions. Now you would say to the same person, okay, that's great, that's great. Now what I want you to do is start with the number 20 and count backwards. And the person will say, okay, 20, 19, 18, 17, September, October, November, December. And they've slipped back into the previous task. They don't have the effort here to say, we've stopped it with the months already, now we're doing numbers. Don't slip back into that month stuff, but yet that's exactly what occurs. You take somebody with frontal damage, you give them what would be called a verbal fluency test. You say, okay, 1 minute, tell me as many words as you could think of starting with the letter F. Great. Now tell me as many words as you could think of starting with the letter M, with the letter P, so on. And you go with letter M, and by the fifth word, they're back to words with F. The previous task intrudes in there. It has trouble organizing, strategizing. We're done with the letter F. We're done with doing the months. Concentrate now. We're doing the letter M. We're doing numbers backwards. Don't fall for the easy version of just saying 11, 10. This is the stuff that the frontal cortex does. This is what it looks like when you are getting damage to the frontal cortex. Okay, so cognitive aspects of that. What's the frontal cortex particularly good at in the cognitive realm? It is making you work and work and work for a cognitive reward way down the line, and that's the entire world of all of you guys already gunning for the perfect GPA that will get you into a good nursing home someday. That is your frontal cortex working to your advantage. That's your frontal cortex doing that, this task of gratification postponement. Do the harder thing. Where am I going to get the energy for it? It's these frontal inputs that's just biasing so I could do the harder pathway rather than the easier. You find this also when you're doing electrophysiological, when you're recording, you're sticking in electrodes and seeing when neurons are excited. Suppose, for example, you've got a monkey and you are recording, you have electrodes both in the visual cortex and some other ones in the frontal cortex. And again, this is one of those tasks where when the bell sounds, bells don't beep, when some buzzer beeps, it means to the monkey now, okay, every time the light goes on, you have to press a lever 3 times and you get a reward. That's the rule. Buzzer means we're starting one of those testing sessions again. Light comes on, hit lever, light comes on, hit lever. So you record from the front, from the visual cortex, and here's what's happening. This is when the buzzer comes on saying, oh, we've just started one of these test periods, and now the light flashes, and the visual cortex activates each time. What's going on in the frontal cortex? The second the buzzer goes off, the frontal cortex activates and it stays up the whole time. What is the visual cortex coding for? Individual examples of this task. What's the frontal cortex coding for? It's remembering the rule. Okay, the buzzer went on, that means now remember, remember, remember for the next whatever period of time, get ready, every time a light flashes, hit the lever there. The task of the frontal cortex is to maintain the rule throughout, transcending the individual examples of it. So you can already see where we're heading with moral development in kids and frontal maturation, and all of that's going to fit in really well, the frontal cortex doing stuff like that. What you should begin to notice is intrinsic in all of this, the frontal cortex is sending these projections all over the brain. The frontal cortex does not code for individual examples of rules, but instead maintains rules for long, long periods. The frontal cortex works really hard. Frontal cortical neurons have very high metabolic rates, and a whole world of neurology thus is built around the fact that frontal cortical neurons are very fragile. They die very readily. All sorts of neurological disorders damage the frontal cortex with behavioral changes that go along with that. Okay, so you've got the wiring, the patterning, all of that, but then at some point you wonder, well, learn all sorts of rules. Back when I was about 3 years old, I learned this rule having to do with, no more diapers, and if you go to the potty, you get M&Ms, and in fact, I sort of have internalized this, and does that mean you need to go to the bathroom now, is internalized that there's a frontal cortical neuron that got excited when I was 3 years old and got toilet trained and has been firing ever since then? No. What you see after a while is the frontal cortical realm of remember, you go to the bathroom when you need to do this, remember, you say the months forward, remember all these sorts of things. At some point it becomes automatic. It becomes reflexive. And what is seen is, at that point, the frontal cortex stops being the area that is active. At some point, instead, it becomes implicit pathways, procedural pathways. It gets stored elsewhere in the brain. What you see in individuals with Alzheimer's disease, where you get a lot of damage to the hippocampus and the cortex, particularly the frontal cortex, what you see is all sorts of things that were learned way back when and learned enough to just be habitual, people can still do. You will have somebody who is demented enough that they could not tell you what decade it is, the name of their spouse, the name of their children, how many children they have, whatever, but this is someone who still knows how to knit. They learned when they were 7 years old how to knit, and now 80 years later they can still do that. This is not the frontal cortex remembering the knitting rules for the last 70 years or so. This is, it became automatic and got moved elsewhere. And a whole bizarre world you see with frontal damage in individuals with these dementias, where some of the things that become automatic are remarkable, suggesting that you've got storage capacity in other places in the brain when you don't have to consciously think about it. When something has become so automatic, you go to the bathroom when you need to void your bladder. Okay, we don't have to think about that anymore. It has now gotten to a pathway like this. Other brain regions, particularly the cerebellum, seems to play a large role in that. Stay tuned. We are going to be getting to a very interesting point about moral development in kids. When do certain moral rules stop having to be coded in the frontal cortex and instead become as habitual as toilet training? We'll see some really interesting implications of that. Okay, so what do you see when you get frontal damage? You get all these cognitive problems there, and these problems with doing the harder but more correct thing cognitively. You see it as well in terms of doing the harder but more correct thing in terms of behavior, social behavior. First classic example of this, they take away your neurobiology license if you don't mention this guy at some point. How many of you have heard of Phineas Gage? Okay, how many of you have not heard of Phineas Gage? Okay, time for Phineas Gage. Okay, but the ones who've heard of him, let's all say this in unison. Okay, Phineas Gage was the first identified individual to have massive frontal damage. Phineas Gage was a foreman on a railroad construction line in Vermont in the 1840s. One day, thanks to somebody or other doing something wrong, there was an explosion of some dynamite which blew a large metal rod through his forehead and out the other side, taking out his frontal cortex in the process. And this was rather dramatic, and this was this large metal pole that went through fast enough that in fact cauterized all the blood vessels. And you can go see that metal pole at the museum in the Harvard Med School Library, where you can also see his skull, which is very interesting because the rest of Phineas Gage is about 20 miles from here, buried in Colma, so I don't quite know how his skull wound up at that end of the country, but in either case, he was buried in San Francisco minus, well, I guess the dean of Harvard Med School swooped in, and before you knew it, the skull was on its way east there with the metal rod. But in any case, okay, so Phineas Gage had his frontal cortex splattered 15 feet behind him, and what happened was, amazingly, because it went through with such force and so fast that it cauterized all the blood vessels, he was actually able to get up at that point. And most remarkably, with a bunch of people from work, he was able to walk 1.5 miles to the nearest doctor, who, being a good diagnostician, took a look at Phineas Gage and tilted his head back and looked at him and he said, "Whoa, you got a hole there in your head." And was sort of looking in more detail and saying, "Whoa, you've got frontal cortex got blown out of your head there." And this was sort of the peak of diagnostic skills at the time. But what happened was the boss there on the railroad line said, "Gage, you know what? Take the rest of the day off. See you tomorrow." So Gage goes home, and the next day he returns, not just figuratively, but literally transformed overnight. Gage, who was this sober, sobrietous, religious man, highly reliable, foreman of this entire workplace, etc., Gage was never able to work a day steadily for the rest of his life. He became this brawling, abusive, sexually predatory, out-of-control individual, and that original doctor, seeing what he turned into, was the first one who said, well, whatever that part of the brain was that got taken out there, whatever it was, that part of the brain reins in our animal energies. And 170 years later, there's not a hugely better definition out there as to what the frontal cortex is about. So Phineas Gage being the official first one, and you learn all about this guy, but very interestingly, about a year ago, somebody found the very first photograph of Phineas Gage, and go look at that online. What's interesting is he looks like a perfectly normal guy. The pole took out his eye along with the frontal cortex, and obviously there was that problem, but this is like the face of somebody from the 1850s, and there's something, I don't know, I found very moving about seeing this face, that everybody learns about Phineas Gage, and everybody has seen his skull and the reconstruction of the accident, and that's right, this was like a regular old person whose life was completely destroyed when the frontal cortex got scattered all behind him there. Remarkable first example of that. Since then, most of the evidence for what frontal cortex is about from damage is older individuals who have stroke damage to the frontal cortex. And what I mentioned, I think, in the limbic lecture, one example of what this looks like was a horrifying case in a facility in the East Bay some years ago where an 80-year-old man who had had extensive frontal damage due to a stroke was found to have raped an 80-year-old woman with Alzheimer's disease. This is what frontal damage looks like in an 80-year-old. Here's something very interesting to consider, and seeing exactly the terrain we're heading into here with this sort of information. Approximately 25% of men on death row in this country have a history of concussive head trauma to the front of their head. Front of the head, where you wind up damaging the front of the brain, frontal cortical damage. And what we enter into here is this whole realm where this stuff is stupefyingly relevant to making sense of criminal behavior in humans. Possibilities of frontal damage. Currently, there is one law that's on the books in the majority of states in this country for deciding when somebody is so organically impaired that they count as having an insanity defense rather than being criminally culpable for their acts. And this is something called the McNaughton rule. McNaughton rule, everybody gets taught that what the McNaughton rule is can the individual tell the difference between right and wrong? This is the gold standard in courts as to whether or not somebody gets a organically impaired insanity defense ruling or not. McNaughton, whose work, that was all of this cutting-edge neurobiology was based on, McNaughton was most probably a paranoid schizophrenic, a guy in 1840 who attempted to assassinate the Prime Minister of England and was so clearly psychotic that this was the first case of the jury formally saying that no, there is something too sick about this man to hold him responsible for his acts. And the clearest thing that came through in that trial was he could not distinguish right from wrong. And the sort of thing that absolutely does in somebody attempting a McNaughton defense in a criminal trial is if there's evidence that they tried to cover their tracks afterward, that they were aware that they had done something which was unacceptable. What you see with people who can't tell the difference between right and wrong, there's no evidence of them trying to cover up their tracks. Where do you see McNaughton rules standardly applied? Severe schizophrenics. And for example, John Hinckley, the person who tried to assassinate Reagan in the 1940s, in the 1980s, but well, I won't go there, but in the 1980s, and he was found innocent or guilty with an insanity defense because he failed a McNaughton ruling, severe schizophrenic. So this has been the gold standard in most of the courts in most of the states in this country. The only way you could be held not accountable for your criminal actions because of organic impairment would be if you can't tell the difference between right and wrong. But then you got a problem, because you get people with frontal cortical damage and they can tell the difference between right and wrong. They know the rules, they can state them for you, yet they can't control their behaviors. And this comes through with all sorts of tests, but you could show this now with people with frontal damage. And for example, here's the M&M test that you give them, and what you've got is something desirable. In this hand you have 5 M&Ms, in this hand you have 1. And the rule is, if the person reaches for the 5 M&Ms, you pull your hand away quickly, and they get 1 M&M as a reward. If they reach for the 1 M&M, you pull your hand away, and you give them 5 M&Ms. In other words, can they be disciplined enough to not reach for the 5 M&Ms and instead hold out and go for 1? You get more of a reward that way. By doing the harder thing, you will get more of a reward. Extensive frontal damage, they never, ever are able to reach for the 1 M&M. They always get pulled towards the easier solution, the easier, more superficial way. There's 5 M&Ms. That's what I want. Instead of being able to do the executive stepping back and saying, if I go for 1 right now, I will get 5. What is remarkable is you get an individual with frontal damage, and they will tell you what the rule is. They will sit there and say, I know what you're up to. You want me to grab the 5, but then I'll only get 1. What I need to do is grab the, and then they go for the 5. They can verbalize the rule right there. They know the difference between right and and wrong. This is not organic impairment of knowing the rules. This is organic impairment of being able to follow the rules. And it is extraordinary what this one feature of what the frontal cortex does, the difference between knowing that there's a difference and being able to activate this pathway instead of that. This is hugely, hugely challenging in the courts. At the time that Hinckley attempted to kill Reagan, every single state in the country had a McNaughton ruling in place. Yeah?
So for those people that just have the damage and know the rules, would they cover up their tracks in the court case so they would be deemed not worthy of the McNaughton rule?
Okay. They would fail the McNaughton ruling, absolutely, because they know the difference between right and wrong.
And they would carry out the action and realizing it was wrong and so try and hide it.
Yeah, exactly. Or if they're disturbed enough, okay, for our purposes, yes, the person will know the difference between right and wrong, but they still cannot regulate their behavior. And this is a huge problem. What you wind up seeing is the McNaughton rule has generally been accepted in most states in this country. At the time that Reagan, the assassination attempt was made, federal criminal rulings had McNaughton ruling in it. Almost all the states had McNaughton, and something about 10 or 11 of them also had an organic impairment of volitional control, recognizing realms of frontal damage. And what was very interesting was in the aftermath of Hinckley being found criminally insane instead of guilty, there were these Neanderthal bellowings all over the country, editorials everywhere about how Hinckley had gotten away with it. Within a month, the federal government, Congress, revoked the ability to have a McNaughton ruling in any federal criminal trial. The vast majority of states in this country, their legislatures promptly leapt into action to repeal McNaughton. And along the way, I think in all but one or two states, the volitional impairment rulings went down the tubes also. And at this point, the vast majority of states in this country, you could have your frontal cortex blown out of the water and you've got 1/2 neuron still functioning there, and that is not relevant in a court of law. An area that desperately, desperately needs some reform. To give you a sense of how bizarre this could look, this dissociation here between knowing the difference between right and wrong and being able to regulate your behavior, this is what it would look like in terms of criminal sort of behavior with frontal cortical damage. And bizarrely, this was actually a law case I was involved with some years ago, where this was an individual who had just been convicted of his 8th and 9th murders. And this was a serial murderer, and he was like a nightmare beyond imagination, what this man was. And this 8th and 9th one had just been 2 boys he had abducted, kept captive for a week, sexually raped, sexually mutilated, and strangled. And this was number 8 and 9. And he had been brought out of a maximum security prison in Florida where he was serving a whole bunch of other life sentences. And this was a case down in San Diego that he was brought out for that one. And the defense consisted of 3 minutes of the defense attorneys getting up and saying, yes, he did it. He absolutely did it. This was the defense. So this was now in the penalty phase, deciding, was this person going to get the death penalty, or was he going to get life in prison without the chance for parole? And the relevant thing about him was, when he was 6 years old, he had had a massive car accident that destroyed his frontal cortex. He spent 2 months in a coma, no prior history of antisocial behavior, no family history of any of it, came out of it extremely behaviorally disinhibited. By age 11, he had assaulted his first individual, first murder by age 13, a completely broken machine. Here's what behavior looks like in somebody with no frontal cortex in this realm. One of the things he also did, in addition to a string of murders, were kidnapping and rape and aggravated assault. And this was one woman who had managed to fortunately survive this. And she'd been abducted by him, where he took her to his apartment and kept her there for a week, repeatedly raping her, beating her senseless, days and days of this going on. And eventually, whatever it is that shifted in him shifted. He had, of course, her wallet in the process of kidnapping her and seeing her name, where she lived. He finally says, okay, time to go, bundles her into his car and drives her home. And as he lets her out, he says, I had a really good time. I hope you did too. Here's my phone number. Maybe we can get together again sometime. And drives away. And no surprise, he was arrested within an hour or so and eventually sort of pinned to a whole bunch of these other ones. This is what it looks like when you got no frontal cortex. What's interesting there is obviously making no attempt to cover his tracks, he was able to verbalize some of these rules and say it was inappropriate, and he was able even to be told the specifics of his own case with other names used and be able to say, whoa, that's not something you should do, that's against the law. At these junctures, though, completely going off the rails. He had an interesting combination, though, which is that there were some elements of the difference between right and wrong aspect of it. The fact that he had his frontal cortex damaged so early in life, what you tend to see is around age 5 or 6 or younger, the person tends to never quite incorporate the rules either. It's not till you get, say, adults who get frontal damage that you get the absolutely pure dissociation between this is not okay to do, this is a wrong thing to do, I am not going to do it, and then goes and does it. He instead had this much more mixed case there. When you get the frontal damage around ages 5 or 6 or younger, you get what is now termed acquired sociopathy. You don't do a great job of incorporating the rules themselves, and you certainly can't act on it. So this is what it looks like with someone who is that broken in this part of the brain. Ironic ending, first jury was hung. We got one person to hold out for organic impairment and give him life without parole. So that was a mistrial, and second jury went through the whole thing all over again, and it took him 3 hours to give him the death penalty. So what's very interesting there is like 25% of men on death row have a history of concussive trauma to their frontal cortex. Really, really interesting. So, but now we begin to see some of those if-then clauses. Here's another individual with a history of frontal damage, and this is a relative of a close friend of mine. And this was someone who, when he was being born, there was a birth complication and they had to use calipers and something slipped and caused frontal damage, and he is frontally disinhibited. This is an individual who is now an adult who is unconstrained by the laws of society. This is an individual who cannot regulate his behavior. What does he do? Whenever there's family get-togethers, he plays the piano way longer than anybody else wants to listen to. He can't pick up the cues that everybody's had enough and wants to go eat dinner. Well, that was great. I think the pot roast is getting a little cold by now. Wasn't that great, everyone? Wasn't that? And just keeps, oh my God, he's out of control. No less frontal damage than this guy did. So here we have this puzzle. We do not have the simple machine output there of, oh, massive frontal damage, this person is a serial murderer. Massive frontal damage, this person plays Scott Joplin for hours and hours until even his grandmother can't stay in the room anymore. What's the difference? I think we begin to see some of our if-then clauses perhaps relevant. The Scott Joplin playing one, upper middle class family, tremendous family support. This guy coming from a family anything but that. We begin to see the, if you have no frontal cortex, but you have tremendous amounts of family support, lots of opportunities, blah, blah, it is going to look different than the massive case of it. Okay. So now, looking at that, what we see is there's just a couple of states and a couple of juries in this country that could deal with the implications of somebody having 99% of their frontal cortex destroyed. All you need to do to see the problem we're up against is what happens if you got somebody who's got 97% of their frontal cortex destroyed, or 94%, or 85%, or finally in our realm where we all just have different sized ones and the person next to you has 5% more synapses there, or 3% fewer reuptake pumps or whatever. That is beginning to get into a realm that is very challenging. Okay, so legal implications there. Enormous ones, and ones where like reform is desperately needed. This reminds me, here is an example which strikes me as historically quite amazing. Okay, so we have the system saying, yes, it is possible to be responsible for your criminal behavior, but here's this one exception. If you happen to have all of these neurons destroyed and you're in Oregon, you can have this criminal defense and it's effective. Oh yeah, there's this footnote. Every now and then something can happen so that you get into a different category than people who've done something awful because soul or evil or whatever terms are coming in there. Really interesting piece of history. 16th century. during a period where if you had an epileptic seizure, you were virtually guaranteed to be burned at the stake as a witch, because there was a medical explanation for epilepsy at the time, which was it was demonic possession, and you were obviously a witch of some sort or other, and okay, so that was the medical knowledge of the time. And if someone was accused of a witch in most Western European countries where the Inquisition was occurring, the rule, the law at the time was, how do you confirm if somebody is a witch or not? You read them the story of the crucifixion, and if they don't cry, they are obviously a witch. And that was the test. That was the legal test. If somebody was not moved to tears by the story of Christ being crucified, they were obviously a witch and would very quickly be burned at the stake. At that point, one very, very progressive physician who was up on the top of behavioral biology insights at the time wrote a pamphlet saying, well, yes, of course, we need to get rid of witches because they're bad news, and of course we should burn them, and this is a very good test. You have to remember, though, that every now and then in some elderly women, the lacrimal glands can atrophy, so they can't cry. So this would be someone who is involuntarily unable to cry rather than they're a witch. You just need to keep that in mind when you do some of that witch sentencing stuff. Sometimes it could be due to this organic impairment business, but the overall structure, yeah, let's get rid of those witches, and that's a very good way of getting at it. That makes no sense at all. I suspect ultimately saying that in a small handful of places, if you have no frontal cortex at all, we're talking about neurology. If you got any frontal cortex, we're talking about morality and soul and even all of that. I suspect it will eventually make as little sense as lacrimal glands drying up. Okay, I'm obviously just on the edge of tirade, so let's take a 5-minute break and we will continue. Frontal cortex of yours, keeping track of all those different rules and keeping you from belching loudly in the middle of a lecture and all those other frontal cortical sort of tasks. What's the time of day when your frontal cortex is least active? Any guesses? Okay, wait, somebody say something clear.
Late at night.
Late at night. When late at night? When you're sleeping. When you're sleeping? REM sleep. REM sleep, your frontal cortex basically shuts down entirely. That's why your dreams make no sense. That's why your dreams, you're doing all sorts of things you would never want to do in real life. The thing about the frontal cortex is that it keeps you from doing and saying the sort of stuff that all of us contemplated various times, but we would die if anybody knew we were thinking that. Or you wipe out the frontal cortex and you do it, or you take the frontal cortex offline in the middle of dreaming, and suddenly that seems like a wonderfully prudent thing to be doing with yourself in the middle of a dream there. That's when the frontal cortex is least active. Okay, so now frontal cortex, looking at one of its most distinctive, interesting things about its function, its development. When does it develop after birth? And I think what I've already mentioned is the frontal cortex is interesting because it's the last part of your brain to fully develop. It is the last part of your brain to fully form all of the myelin on its axons. It's the last part to get its full large complement of synapses and branching connections and such. It's the last part of the brain to develop. When does the frontal cortex, on the average, completely mature, go online for the first time? Around age 25, which is astonishing, which, among other things, should be reckoned in the context that probably all sorts of you guys still have a whole lot more myelin to lay down there in the frontal cortex. It is the last part of the brain to fully develop. Some immediate implications of that: if it is the last part of the brain to develop, it is by definition the part of the brain least constrained by genes. And it is the part of the brain most sculpted by environment and experience, which is real interesting given that it is the most definedly human part of the brain. So, frontal cortical development in kids. What we've already heard is by age 5 or younger, get frontal damage and you get this acquired sociopathy. You don't get as clear of a dissociation between, you know what the rules are, you simply can't carry them out. It's more of a mixed bag at that point. Frontal development after that. The frontal cortex works in a very interesting, perfectly logical way in teenagers, as follows. When you look at frontal activity and the extent to which it is being driven by dopamine with one of these brain scanners, take an adult and take a teenager, and they each have circumstances where they're doing some task and they get a reward, and some of the time they get a smaller reward than they think they deserve from the amount of effort they put in, and some of the time they get an unexpectedly large reward. Circumstance where the individual gets a bigger reward than anticipated, dopamine goes up in adults and drives frontal metabolism to a certain extent. Dopamine goes up much higher in the teenager. Now, a circumstance where the task is being carried out and you don't get the reward. Dopamine goes down in an adult, frontal metabolism goes down a bit, dopamine goes down much more in the teenager. The gyrations are much more extreme. The dopamine-driven metabolic changes in the frontal cortex are more dramatically large for reward, are more dramatically having the floor fall out under it for lack of reward, for disappointment. It's a system that is simply less regulated. And this fact that the frontal cortex is the last maturing part of the brain had to do with one of the wisest things the Supreme Court has done in a long time, which was about 10 years ago, when they made a ruling that individuals who are under age 18, when they carry out a capital crime, you cannot have the death penalty applied to someone for a crime they did between ages 16 and 18. Because explicitly stated in the court decision, the brain and the regulatory areas of the brain are not fully mature at that point. The most neurologically informed the Supreme Court has been in a long time. Again, the McNaughton rule, which is the backbone of the criminal defense legal system in this country, is based on 170-year-old neurobiology. So this was a major leap forward in jurisprudence meets neurobiology in this country with the Supreme Court ruling. Of course, one might ask is, so what exactly happens in the brain on the morning of your 18th birthday that now makes it okay to put you to death, where the science simply doesn't back it? But at least that recognition, the Supreme Court actually dealing with the fact that a 17-year-old does not have a normal frontal cortex yet. What else goes on? Thus, by the time you get a fully online frontal cortex around age 25 or so, one of the truly depressing things out the other end of it is the frontal cortex is the third most vulnerable brain region to normal aging. Bummer. That is a drag. What that winds up meaning is you have spectacular impulse control for about 3.5 weeks on your 25th birthday, and it's all downhill from there. There's a motor system in the brain called the substantia nigra, which loses most of its neurons with aging. That has something to do with the tremor of old age, Parkinson's disease. The hippocampus loses a substantial percentage of its neurons with age. That has something to do with some of the memory problems. Number 3 on the list is the frontal cortex. Frontal cortex loses lots of neurons over the course of aging. And what you see then is all of those tests of cognitive function, of frontal functioning, they all have to be age adjusted because people as they get older have more trouble doing this, inhibiting the overlearned response, preventing something from intruding previously. There's fewer of these projections coming in there. And what does this begin to explain? This is this whole world of grandmothers telling you exactly how hideous they think your new hairdo is. That's the world of disinhibited 80-year-olds speaking. And what has always been the case in that literature, it has always been interpreted in a social, psychological, maturational framework. By the time you get to a certain age, you finally accept, this is who I am. I'm not in middle school anymore just trying to be popular. If I need to march to a different drummer, so be it, because I'm at peace with who I am. I accept myself. It's not that, it's the brain damage. It's the brain damage that kicks in at that point. That being a feature of normative aging. Now, where else do you wind up seeing abnormalities in frontal function? Other individual differences. One personality style where you see elevated frontal metabolism. And this is people with what's called repressive personalities. These are individuals who are highly regimented, highly disciplined, highly capable of controlling their behavior. These are individuals who do not express emotions very readily. They're very bad at reading emotions in other other people. They're not depressed, they're not anxious. In order to be labeled with a repressive personality, those are rule-outs. You have an extremely structured life. These are the people who can tell you like everything they're planning to do for the next 3 years and it's already scheduled out. This is the roommate who always has all the work done 3 weeks before the due date. This is the person who makes you crazy because you wish you could be half as disciplined as they are. People with personalities like this, elevated resting metabolism in the frontal cortex. So which sort of people have far lower than normal metabolism in the frontal cortex? Any guesses? Shout out. Thrill seekers, yeah, thrill seekers, it seems to be more at the dopamine end of things, and the Zebra book considers that at one point in there, when it's more manifest in how are you going to pull off stuff like this, sociopaths have much lower than normal metabolic rates in the frontal cortex. And in fact, in a couple of weeks, there's a guy coming to give a lecture, and I'll announce in here when and where, who's one of the people doing the most interesting work with this. What this guy has is a functional MRI machine on a trailer which he drives around from one maximal security prison to another throughout this country. Really interesting research on violent individuals who are or aren't sociopathic, decreased frontal metabolism. But now something interesting. You take a sociopath whose resting metabolic rate in the frontal cortex is lower than normal. Now you give them a task which demands a certain degree of frontal function. Not, oh, be a law-abiding citizen in society, but something like the tell the months of the year backwards as fast as you can go. And what you see is in order to generate the same level of performance, they have to activate more of the frontal cortex than other people do. In other words, under resting circumstances, there is a hypometabolism in the frontal cortex, and in the rare, relatively unemotional circumstances where a sociopath does want to pull off a lot of regulation of behavior, they've got to recruit a lot more of the frontal cortex to do it. It takes more work to do. Other aspects of frontal cortex. Not only are kids not dealing with a whole lot of frontal cortex, other species are not dealing with a whole lot of frontal cortex. Again, humans have more frontal cortex proportionally than any other species. There is no chimpanzee on Earth who could master the 5 M&M, 1 M&M task, and that is regularly sort of used as a test for frontal function on them. Chimps cannot do it, because it is simply too tempting to reach for the 5 M&Ms because it's right there. Interesting assay of how many frontal neurons a chimp does have, though, which is now instead of 5 M&Ms and 1 M&M, 5 chips of wood and 1 chip of wood. Reach for the 5 chips of wood, you get 1 M&M. Reach for the 1 chip of wood, you get 5 M&Ms. Every chimp can do it now. They can all do it now because they're just looking at these pieces of wood and they could remember, that's right, don't go for the 5 pieces of wood, go for the 1 piece of wood. When it's chocolate, though, in front of them, it smells so great, and how can you expect them to keep track of the rules? And it's just the 5, and before you know it, they've done the wrong thing. If you take away some of the viscera of it, if you step back sensorially, if you substitute this in-your-face chocolate for these little bits of wood, chimps on the average have enough frontal function to be able to pull that task off. Kids, again, could never do this. And this is one classic sort of developmental test. You take a kid, and they're in a room, and you put a marshmallow there, and you say, okay, does people know this one? Okay, so do people not know this one? Okay, so here's what you do. You put the marshmallow there, and you tell the child, okay, I got to go out of the room for a little bit. You can have the marshmallow whenever you want, but if you haven't had it, by the time I come back, you can have 2 marshmallows. In other words, how many synapses do you have in your frontal cortex? Because that is spectacularly predictive of frontal metabolism in these kids. How long can they hold out through doing the harder thing that gets more of a reward? What those studies also are showing is the length of time a kid could hold out on the marshmallow test when they're 5 years old is predictive of SAT scores. Many years later is predictive of all sorts of aspects of the trajectory of that frontal development. Here's an even better assay for frontal function in a kid. And this one, I think this is even more informative than the marshmallow test. Here's what you do. You got your 5-year-old and you play hide and seek with them. And the deal is you're the one who hides, who counts first while they go and hide. And what you do is you finish counting, and then you loudly, excitedly say, here I come, I'm going to get you, here I come. Oh, where are you? And then they instantly say, right here under the piano. Because they don't have enough frontal neurons to keep themselves from saying that. They can't stop themselves from saying, here I am, falling for that. Now they switch and it's their turn to count, and they count, you count up to 10, and they go 7, 8, 9, 10, 11, 12, 13, 14, because they're so excited to have discovered recently there's all these numbers that why not count all of them off and show, and they've long forgotten you're supposed to stop at 10. They can't inhibit that response. This is what frontal function looks like in a kid. So marshmallow tests and hide and seek tests. How's this, though, for taking that charming world of 5-year-old regulation and putting it into a much more depressing developmental context? Studies by now showing at age 5, already kindergarten-aged kids, there is a relationship between your socioeconomic status and the thickness of your frontal cortex and its resting metabolic rate. What's the part of the brain that has some of the highest levels of receptors for glucocorticoids? The frontal cortex. What do glucocorticoids do to the frontal cortex? They atrophy neurons there. So what you are already seeing is get yourself an unfortunate, imprudent decision in terms of which family you got yourself born into and be raised with the stress of poverty. And by age 5 already, there are socioeconomic differences in the size and the activity of the frontal cortex. And that is, I think, one of those factoids that should have like people rioting at the barricades in terms of how screwed you are, how early on in life, in the most like straightforwardly neurobiological way by some of these oddities of experience and bad luck. Okay. So looking finally at the frontal cortex, one thing to ask at the end of the day is, so frontal disinhibition, why don't you see with people with massive frontal damage, instead of them becoming serial murderers, why don't they become like serial people getting married? Why aren't they serial standing on street corners giving away their money and announcing their love to the whole world and doing equally disinhibited things in that realm? It's not clear. It's not clear why this is so much more tightly involved in regulation of stuff going on in the amygdala. Okay, so as implied though by this arrow, it is not one direction of inputs there, it is bidirectional. What you also see is a lot of ways in which the amygdala can regulate the frontal cortex. And what you already can guess is the projection from the frontal cortex to the amygdala is inhibitory. The projection from the amygdala to the frontal cortex is inhibitory. The frontal cortex is trying to get the amygdala to restrain itself. The amygdala is trying to get the frontal cortex to stop sermonizing at it. And what you wind up seeing is, in rats and primates and humans, there is an inverse correlation under resting conditions between the metabolic level in the amygdala and the frontal cortex. They move in opposition. They move in opposition, and what you see is, what are the circumstances where, in effect, the amygdala is going crazy enough to be silencing the frontal cortex? That's the world in which you are making astonishingly bad decisions about things during moments of great duress and arousal that you spend the rest of your life regretting. That's a world of the amygdala getting very inaccurate, rapid-fire information and being able to silence the frontal cortex, and then out comes behavior that is really unregulated, the frontal cortex and the amygdala, in a sense, constantly wrestling in terms of their sort of reciprocity. So what happens when somebody has learned to be afraid of something, and slowly over time they learn that in fact this thing is not fearful? They habituate to this fear conditioned response. They habituate to yoking, this buzzer means I'm going to get a shock. They extinguish the behavior, that's the term given for that. You gradually see the amygdala activates less and less. Ooh, play the buzzer, play the tone that you've been conditioned to associate with a shock. Amygdala goes crazy. No shock this time. Do the buzzer again, no shock, not quite as active. Next time, not quite as active, and it slowly habituates away, destroy the frontal cortex, and the amygdala never habituates to a learned response, a fear-conditioned response which is no longer fearful. It can't learn to stop being afraid. So another realm of this reciprocal inhibitory relationship between the frontal cortex and the amygdala. Okay, final bit here in terms of their interactions. The easiest way to frame it is each inhibits the other. They work reciprocally. There are circumstances, though, where both the frontal cortex and the amygdala will activate. Because all you have to think are of some circumstances where whatever your cultural conditioning is, doing the harder thing, which is the right thing, is also the scarier thing. Just think what it takes to have somebody blow a whistle and you leap up over the top of your trench in World War I, and you're going to be dead 10 steps into running towards the other trench line. At some point, the frontal cortex is in fact stimulating the amygdala very strongly to produce its behaviors. That's showing a circumstance where that is indeed the harder behavior. It is simplifying to say that they always work in opposition, but as a general rule, that's happening. Okay, what this allows us to do now is step back a bit and now look at another brain region. One which is in effect working in opposition to the amygdala in another realm, which is the septum. The septum, you remember the septum, the hippocampus, sends its loop through the fornix down to that septum thing. In some manner, the septum inhibits aggression. In the same way that simplistically the amygdala mediates it, the exact same sort of evidence, lesion studies, stimulation studies, recording studies, for reasons I don't fully understand, the septum has never been really a hotspot for a lot of research. Nonetheless, it in some ways works in opposition to the amygdala. You could now sit with one of those circuit diagrams of the limbic system, seeing who's connecting to who, and you could see what sort of wiring there must be for the septum to try to silence the amygdala, what the circuitry there would be. Back to that limbic rule, all these limbic structures are trying to yell at the hypothalamus and get it to listen to them and not to the other regions. Another area implicated in aggression, the lateral hypothalamus. Lateral hypothalamus, the subject of a huge amount of research in the 1960s, people interested in aggression, and then people acted like ethologists and learned the thing that we've already talked about a bit in here, which is, oh, actually, the lateral hypothalamus has nothing to do with aggression. It's got to do with predatory behavior. When a rat leaps on a mouse and shreds it, that's not an act of aggression, that's an act of foraging. Oh, lateral hypothalamus, food acquisition, not aggression. Tons of research in the 60s went down the tubes when people began to figure that out. Now, flipping to the other side of all of this stuff, rather than the aggression realm, the empathy realm, the compassion realm, where are the structures coming in? And we already know an area from the sex lectures that is pertinent, which is the anterior cingulate, sitting just behind the frontal cortex. And we already know about some of the things that it does. Remember, that's the part of the brain. Somebody pokes your finger, it activates along with your pain sort of receptor pathways. You watch the finger of your loved one gets poked with a pin, anterior cingulate activates as well. That is the part of the brain where literally and not just metaphorically you feel the pain of other individuals. How's this? Now a study, this was done recently by a guy at Harvard named Josh Green. What he does is he puts people in brain scanners, functional MRIs, and he gives them one of the great horrifying moral decisions that ever sort of actually occurred in history, which was the old scenario that you and a bunch of people are hiding from the Nazis who were nearby, and there's a baby with you and the baby who keeps crying, and it is clear if the baby keeps crying you are all going to be caught and killed. Is it okay to smother the child? And this wonderfully hypothetical, let's write a doctoral thesis dissertation on this problem here, was one which was a human sort of decision that had to be made endless number of times. What would you do in that circumstance? And what he shows in these studies are that people who activate the anterior cingulate less when they are contemplating this decision are more likely to reach the decision that it is okay to smother the child. You see that in these studies. Something about the feeling the pain element, the empathizing, the something about that, when it is not as extreme, that is a predictor in these studies of individuals who will vote for the smothering. All of this has given rise to this view that a lot of what's happening between the cortex and the limbic system is a whole lot more complicated than this old dichotomy between thought and emotion, and the cortex is about thought and the limbic system is about emotion. What is clear is instead they are inseparable. This whole notion brought up already, that guy Damasio, major figure in the field, this book of his called Descartes' Error, where he goes over Descartes' notion of the separability of thought and emotion, and how in terms of brain function that is not remotely the case. In some realms, you can partially separate cortical function, frontal cortical function, from limbic function. One example of this, and this was a classic study done by that same guy, Josh Green, and this was when he was still a graduate student, involved making use of people in a brain scanner with what's apparently like a classic test in, or a classic puzzle in philosophy, the runaway trolley problem. Here's the scenario. There is a trolley which is somehow broken loose from its brake. It is rolling down the tracks where it is going to roll over there and kill 5 people. First scenario, you have a choice. You can pull a lever which will cause the trolley to be diverted onto a different track where it will kill 1 person. Is it okay to pull the lever, saving these 5 people and 1 person getting killed? Second scenario, you have the option, you're standing behind this big beefy person and you can push them onto the track where the trolley will hit them and kill them, but it will stop it from hitting the 5 people. Are you willing to kill 1 person in order to save 5? And something that is shown in these studies over and over is like 75% of people are willing to pull the lever, 25% of people or so are willing with their own hands to push somebody onto the track. The math, the logic is absolutely equal, but this is always interpreted as how we make different sorts of decisions when it is a much more visceral in your face. You are going to have to push this person to his death with your own hands versus something as impersonal as pulling a lever, sitting in a cockpit in a military base in Las Vegas and killing people on the other side of the globe. How salient in your face is it? You get very different responses. And what Green showed in his study was, have people contemplating whether or not to pull the lever, it's the cortex that's activating, predominantly frontal cortex. Have people decide whether or not to push with their hands, it's predominantly limbic activation. Another version of this has been researched by a guy at Dartmouth named Oliver Goodenough, again brain imaging, and he is both a neurobiologist and also on the law school faculty there. And here's the sort of study he does. You will see the equivalency of it. Put people in a scanner and they've been going through a mock jury trial, and what they now receive on the scanner are the judge's orders to the jury before they go and deliberate. First version, the judge says, remember what you were here for. You may have your feelings. You may have your feelings about the person and what they did or what they didn't do. But at the end of the day, your job as a juror now deliberating is simply to decide, was this law violated or not? This is not for you to decide if it's a good law or not. This is simply, was this law broken? Second scenario, the judge stands there and says, okay, as you go and deliberate, remember, of course, what the law is, but remember, at the end of the day, what is this system about? It is about protecting the weak from the powerful, and you are a decision maker at this point. 2 totally different. One is rule-bound, one is empathy-bound. People get the first sets of rules, cortex is activating, second set of rules, limbic system is activating. So those are some domains where, in fact, they are quite separable. What you see, though, is that there are all sorts of domains in which it is a completely ridiculous dichotomy to make between, pure abstract cognitive decisions and these messy, yucky, emotive, limbic sorts of ones. Instead, tremendous amounts of interactions between the two. One domain where you see this, which is what happens when you begin to damage some of these structures, you change the flavor of the decisions that are made. Get people with frontal damage and give them the runaway trolley problem, and they are far more likely to say, yes, it is okay to push somebody onto the tracks. They get a far more utilitarian decision. Equally interesting, and the same sort of punchline, studies where a technique that's now just being worked out called transmagnetic stimulation, where you can decrease the activity of certain cortical regions for a couple minutes at a time, turn off one subregion of the frontal cortex in people, in volunteers, and in various game theory games that they're doing, they become a lot more utilitarian, they become a lot more selfish. So modulating interactions between there, crosstalk between the two. In some ways, the most interesting demonstration for me of the ways in which these are not separable, this thought from emotion stuff, is this really interesting domain of how the human brain does metaphor. Okay, so we get to symbols, we get to abstract things, we get into a world where we have a legal system where not only can we judge that somebody has done something wrong to somebody else if they have murdered them or stolen their possessions, but they can be viewed as having done something transgressive if they've ruined the reputation of somebody else, if they've stolen the ideas of somebody else, plagiarism. This is a very abstract world of judgments we have. These are very symbolic realms of decision making we are often into. Yet, we have this problem that we have this very old evolutionary brain that did not necessarily evolve for doing symbols and metaphors. And one of the things you wind up seeing is when the brain evolved the ability to do some of this more metaphorical stuff, it had to make use of the old circuitry that was there. And thus what you wind up seeing is very often when dealing with extremely abstract issues of decision making, we treat some of the metaphorical components as if they were absolutely real. What would be an example of this? Here's one very cool study that was done recently. Okay, so your body and your brain is very wired up for doing temperature regulation. Ooh, this is hot, this is cold, these are different temperatures, there's a whole like metric and temperature sensitive receptors, and there's a whole circuitry thing, and it's going about the very physical task in the very real world of telling something about temperature, oscillation of ions, or whatever. Get a hold of this study. Somebody is coming up for what they believe is some sort of psych testing that they have volunteered for. They get in the elevator to go up, and the actual experiment is started in the elevator. Somebody working on the experiment comes in, and they're holding a whole bunch of books and barely holding on to them, and they're having a cup of something, and they ask the person, can you do me a favor? I'm about to drop this. Could you just hold this cup until we get up to the 4th floor? In one case, the cup is iced tea. The cup is cold. In the other case, the cup is warm tea. Warm. So the person spends about 15 seconds holding either this cold cup or this hot cup, and the person thanks them afterward, and out they go, and then they are asked to evaluate the personality of the person they just interacted with in the elevator and hold the warm cup, and you rate the person as having a warmer, more expressive personality. No. Temperature, we're talking about like how fast molecules are oscillating. That's what temperature is. Warmth, that's just a metaphor. They get intermixed. When brains had to invent dealing with things like how warm of a personality somebody has, or even something as nutty as how warm is the color of the carpeting in this room, where are you going to stuff it? In some way, it is hijacking some of the far more literal pathways of storage information in the brain. Another example, here is a wonderful one. We already know that the same part of the brain, the anterior cingulate, that will tell you that your finger was just poked, is telling you that somebody else's finger was poked. You are feeling their pain in the same part of the brain that is doing pain in a literal sort of way. Another case of the brain kind of mixing metaphor and symbol with the real thing. Here's a particularly interesting version. Go get yourself exposed to some totally rotting, smelly carcass, or inadvertently take a bite into some truly rotten food, and you will have an area of the brain activate called the insular cortex. And what that does, in every species looked at, is it processes foul, disgusting stimuli. Disgusting, spoiled food, a rotten smell, all of that. That's what the insular cortex does. And no doubt there's tongue receptors telling you bacterial loads or acidity of this rotten food or some such thing, and that's what this part of the brain does. Now, sit down a person and tell them a story of somebody being totally mistreated by somebody powerful in some completely exploitative, horrible circumstance, and the insular cortex will activate. Have somebody play some game with somebody else, one of the prisoner's dilemma type games, where the person totally stabs them in the back, the person they're playing against, and gets away with it and makes some really exploitative, rotten gesture, and the insular cortex activates. Sit somebody down and say, in the control group, tell me about some event that happened when you were growing up, versus the experimental group, tell me about a time when you were growing up that you did something really awful to somebody else. And the person describes that circumstance, and the insular cortex activates. What does this part of the brain do? It's saying, oh yes, this food is full of maggots and does not taste very well, but it also does moral disgust. When you are feeling disgusted with how someone has been treated, when how you've been treated, it activates. When you are having moral self-disgust, recounting something awful you did to somebody, this part of the brain activates. My God, don't they realize up there this is a metaphor? You're not really eating rotten food, and every language on earth has words referring to moral failures with words denoting gustatory repellent stimuli. I am disgusted by what you did. The fact that they did this, when I hear about what they did, it makes me nauseous. Something about this smells rotten. Every culture has terms that intermixes literal sensory disgust with moral disgust. And what that's telling you is that when humans came up with something as fancy as moral transgressions, where are you going to stick the sense of outrage you feel when there is a moral transgression? I know, let's hijack the part of the brain that tells you you're eating some rotten food. Shoehorning into there. Now what you see is it is possible for us to begin to confuse on which level those areas are working. Another study, amazing one, a couple of years ago. Here's what was done in the study. You take people and you put them through their paces of either telling me something wonderful you did when you were a kid, something neutral, or some moral transgression you once had. Tell me all about it, and then afterward saying, well, thanks for participating in this, and tell you what, we can't pay you, but we can either give you this pen set, or we can give you this nice flash drive, or we can give you this little soap set of scented soaps or whatever, and have people talk about their moral failings, and they're more likely to choose the soap afterward. People want to wash their hands of their sins. And starting with Pilate washing his hands of whatever, this is an intermixing of metaphor with reality, showing how clearly this was the case. Now what they next did in the study was had people wallow in recounting something awful they had done to somebody else, and then they were allowed to go to the bathroom, and I don't quite remember how they did this, if they had cameras in the bathroom, which I kind of suspect they didn't, or if they weighed the soap afterward or something. But people who had just gone through the moral transgression recounting were much more likely to go in the bathroom and wash their hands at that point. But now what they had were people who had done the moral transgression recounting. Either they were given the opportunity to wash their hands afterward of it, or they were not given the opportunity. Now, sitting in the test room, what happens is the staged thing. One of the people working on the project comes in holding a whole bunch of books and accidentally drops them, and a bunch of pencils scattered all over the floor. If you were allowed to wash your hands of your metaphorical sins in the previous few minutes, what they showed was you were less likely to jump up and help the person. People translating a sense of being morally soiled into being an imperative of helping somebody else. Let somebody go wash their hands of recounting the awful thing they did to somebody else, and they're less likely to help people afterward. What I think we're seeing here is this amazing intertwining of us doing some of our most abstract judgments and decision makings and decisions about behaviors or not, where we just got these old ancient mammalian brains that does rotten food, doesn't do rotten ethics. You've got the systems confused. What this begins to speak to is work by a very prominent person in the field, a guy, University of Virginia, Jonathan Haidt, whose work emphasizes just how much moral decision making is not decision making, how much it is affective decisions, showing first with brain imaging how often you are getting the affective, the limbic, the disgusted cortical levels of response before you have the decision making. Argument being, And there, it is affect driving the decision making rather than the other way around. But what he also points out is the frequency you give people scenarios, and he's done really interesting work with this, where you give somebody a scenario where it just strikes you as wrong. Here are two of the ones that he hears, three of the ones that he uses very often in the studies. First one, you describe a pair of siblings. They are grown up, they are post-reproductive. She has gone through menopause, he's had a vasectomy, whatever, and they are in love and not in the platonic sibling way, and they want to have a sexual incestuous relationship. Is it okay for them to do it completely in private? Second scenario, your elderly grandmother says it is absolutely fine with her to slap her in the face right now. Do you feel like it is okay to do? Third scenario, one that he brings up, having to do with burning a flag and stomping on it, something laden with symbolism, but at the end of the day is nothing more than just some cloth. Another one he brings up is, you're hungry, your pet has just died, why not cut him up and eat him? And in all these cases, what you have is exactly the responses all of you just had in there, and these insular cortical neurons are popping out of people's ears all over this room. And then what he does is say, well, what's wrong with that? And people really have a hard time giving a rational explanation. This whole framework that he has developed, which most of the imaging research agrees with, that people make their affective decisions long before their more cognitive ones. The cognitive ones are catching up afterward, trying to figure out, well, why is it so important that you cannot step on some cloth that has this pattern on it, but it's okay to step on cloth with it? Why is that something worth putting in people in jail for? It just doesn't feel right. And I think what that has much to do with is how much of the coding of the abstract stuff has to be stuffed into ancient brain pathways that's telling you about very cold things instead of cold personalities, very disgusting foods rather than disgusting moral acts. We are dealing with a very ancient brain, and one that's not very good yet at separating sort of a limbic world from a more cortical one. Okay. Couple more pieces of this. Final piece in terms of making sense of the neurobiology, which is now you look at parts of the brain when somebody is committing an aggressive act and you show neurons get activated there. And well, that's kind of interesting. All sorts of hypothalamic nuclei, midbrain, brainstem, those reptilian parts of the brain from the other day. You see that happening and you say, well, someone does something aggressive and they activate. That seems to be interesting, that seems to be pertinent, and it winds up being not pertinent in the slightest. Because what you see is those are the same neurons that would activate if you are running for your life. Those are the same neurons that would activate if you were running joyfully to meet someone. Those are neurons that are just doing the nuts and bolts sympathetic nervous system stuff. If you were running for your life, or if you were running towards someone you love, and those are totally different emotional states, nonetheless, your heart has to be beating faster and your diaphragm has to be doing something different. These are non-specific pathways of activation in the sympathetic nervous system. As has been stated, if you were recording from some of these sympathetic nuclei in the midbrain, if you were recording from them, you cannot tell the difference whether a person has just murdered someone or just had an orgasm. In both of those cases, neurons have to be doing very similar things. There's a whole realm of non-specificity to arousal. And this brings up a really important quote, and one that I think will run through all of these aggression sections here. A quote from Elie Wiesel. Elie Wiesel, concentration camp survivor, Nobel laureate for his writing. Elie Wiesel, extraordinary man, who has this famous quote which goes as follows: "The opposite of love is not hate. The opposite of love is indifference." And the way that he uses it is in sort of a historical framework. The opposite of love is not hate. The greatest harm you can do to someone who has been a victim of something is to be indifferent to their history, to deny that it has happened, to see it not be an imperative to make sure it never happens to anyone else again, etc., etc. The opposite of hate is indifference. Applied to physiology here, it is absolutely the case. When you look at what the sympathetic nervous system is doing, when you look at some of the stress hormones, love and hate are not opposites in the slightest. They are physiologically very, very similar. What I think that also tells you is how readily some humans psychopathologically can confuse the two states. When you look at some of these brainstem, hindbrain, spinal areas during these acts, love and hate are not opposites. They are very related to each other. Okay, jumping forward in the last couple of minutes, what we now have is looking at what hormones are doing to this. Hormones in terms of the short-term hormonal environment, not early in life, the short-term hormonal environment. And what we have to deal with, of course, instantly if we're going to bring up hormones is, so what's the deal with testosterone? What does testosterone have to do with aggression? Why is it that in virtually every species out there, males are more aggressive than females, males have more testosterone than females do? All you need to do to make sense of this whole section here is take everything from last week concerning testosterone and sexual behavior and just substitute aggressive behavior for sexual behavior. It's the same exact rules. Yes, testosterone is required for the full expression of aggressive behavior in males of most species. How do you tell? Subtract it out, the castration stuff. After castration, do levels of aggression go down to 0? No. The same thing as last week. The more prior experience one has being aggressive, the less of a drop in aggression there is after testosterone levels are removed. Put back 100% the normal levels, aggression is reinstated. Put back 10% the normal levels, reinstated to the same extent, 200% same extent, same exact rule. Testosterone is needed for the normal expression of behavior, but it is not necessary or sufficient, and your brain, your limbic system can't tell the difference between moderate, medium, and very high levels of testosterone. There's no way you could look at an individual's testosterone levels, and because it's 2 units higher than it was last week, or higher than the person sitting next to them, to make any sort of prediction about who is going to be more aggressive. When you see a correlation between levels of aggression and levels of testosterone, it's the behavior driving the testosterone, not the other way around. How does this translate into physiology? Here's one example of this in terms of studies. Take 5 rhesus monkey males, and this was a classic study that was done, put them together and they form a dominance hierarchy. Number 1 beats 2 through 5, number 2 beats 3 through 5, so on. Take number 3 and pump them up with testosterone, pump them up with insane amounts of testosterone, and what you will see is he will now be involved in more fights. Does that mean that number 3 is now threatening number 2 and number 1? Absolutely not. What's going on? Number 3 is being a nightmare to numbers 4 and 5. Is testosterone changing the structure of aggression in this group? No, it's exaggerating the pre-existing social structure. What testosterone does is modulate, it amplifies. It does not turn on a radio of aggressive music. It increases the volume if and only if it is already turned on. What does this look like in terms of the biology, getting down to the neurobiology level? That whole business, raise testosterone levels, and the amygdala gets a lower threshold for deciding that a face looks threatening. Put somebody in a brain scanner and flashing up subliminal faces, and it takes less of a scary face, one that would be borderline, higher testosterone levels in someone, amygdala activates more. How would this look like on a cellular level? Back, remember, with that business about action potentials, the neuron has an action potential, and then for a while afterward, it enters a refractory period. It is silent for a while afterward. What does testosterone do on the level of single neurons in the amygdala? It shortens the refractory period. It makes it possible for the neurons to fire more times per unit time, thus asking the question, what does testosterone do to electrical activity in neurons in the amygdala? It does nothing. If and only if the neurons are already excited, testosterone will increase the numbers of them. Testosterone does not cause, it amplifies. And what it mostly amplifies is pre-existing social structures. Okay, you notice there that I was also being very careful in saying on the average, males are more aggressive than females, and all sorts of species out there on the average, males have higher testosterone levels than females do. The one great exception to this, which is briefly touched on in the Zebra book, which is one of the great topics in all of endocrinology these days, is spotted hyenas. Hyenas are weird animals. Hyenas have a totally different worldview thanks to a bizarre neurobiology. Among spotted hyenas, females are dominant to males. Females are bigger than males. Females are more muscular than males. Females are more aggressive than males. Females have higher testosterone levels than males do. And you look at the private parts of a hyena and you cannot tell who is which sex. Female hyenas have androgenization. They have enlarged clitorises, the size of penises in males. They have something that looks like a scrotum, which turns out to be compacted fat cells that form these scrotum-like things, and they look just like males. And over the years, as part of my field work, I spent some years sharing camp with a guy who is without question the world's expert on like hyena clitorises. And this guy would bring in some anesthetized hyena, and he would have to look at this thing for 15 minutes with like calipers and like night viewing goggles and stuff to finally decide its gender. Hyenas are this very interesting case of a sex reversal androgenization. Females produce very high levels of androgens in their ovaries, and you've got the sex reversal system with the following thing. Unlike in most species of carnivores, what happens in lions, for example, males eat first, followed by females, followed by cubs. Most lion cubs starve to death in the first year of life. Among hyenas, because of the sex reversal system, cubs eat first, followed by females, followed by males. The kids survive that way, a wonderful sort of mutation in terms of doing that. And what you get as a result is unavoidably you get a masculinization of the genitalia in the females. And what you wind up doing is it winds up having a different signaling purpose. In most species, what happens among male primates, for example, when males are trying to display their dominance, they get an erection, wave their penis around, and look how tough and scary I am. And that's due to a certain wiring of the autonomic nervous system. In hyenas, it works just the opposite. Males get erections when they're terrified. Because you think about it, males are lower ranking than females. Females spend all their time ripping off the males who have just hunted something. Females terrorize the males. So you're some male sitting there, and here comes this terrifying female. What do? You say, don't hurt me, I'm one of these males, I'm not threatening, or whatever. That in males, what you get is you get erections when you are under stress as a subordination gesture. What do females do? Low-ranking females get clitoral erections when they are being threatened by high-ranking females, a total sex reversal system. So hyenas can either wind up telling you, we are breaking out of these stereotypical role gender expectations, and that you can have a species where females are dominant and more muscular and more aggressive, but at the end of the day they are like that because they are even more hormonally like males than males are. Final amazing thing about them. And this is a story of this friend of mine, this guy who's been studying hyenas for 30 years, and he's like incredibly knowledgeable about hyenas, and this was something that really makes you stunned at what sort of people there are in the government thinking about things here. So one day, he's from Berkeley, one day he's in his office there, and he gets a call, and it's from some Army colonel. And the Army colonel says, oh, we're having a conference, and we're having a whole bunch of carnivore biologists coming to it. We're going to have a great time. We're having this conference of carnivore biologists, and we want you to come to it. My friend says, you're from the Army? What are you talking about? Do you know what I study? And the guy proceeds to show him that he knows exactly what he studies and what his social security number is and how many cavities he has and how much unpaid taxes. And he says, so all of America's carnivore biologists are coming to this meeting, so come to this meeting, we're going to have a great time. It's going to be at this hotel in Arizona. Come, you're going to have a terrific time. So my friend decides, why not, and goes to this and winds up in this place, and here's this conference with all of America's carnivore biologists and these 3 Army colonels sitting in the back with these sunglasses on. So all the carnivore biologists are fairly confused about what's up here, but nonetheless they sort of settle down and they start doing their scientist thing, giving talks to each other, and the army guys are sitting in the back there, and like there's 2 days worth of them just sitting in the back saying nothing, and finally all the carnivore biologists get all upset and say, what are you guys doing here? What are we doing at a conference paid for by the US military? And they finally say, okay, you're such great guys, we're going to tell you actually what we're really up to here. You know, we're from the military, we're actually from the tank corps. And what we have is we're designing these new walker things. You remember in the Star Wars movie, in the second one, they had those machines that looked like the elephants that could walk and all of that. Well, we want to build them. In order to build them, we have to know how animals locomate, how they move, how they walk. And you guys study carnivores, and carnivores run around a lot, so we want to hear you guys tell us like how your animals move when they're doing things like hunting. And America's carnivore biologists listen to this and say, this makes no sense at all. You want to learn about locomotion in animals, you get like bioengineering people, you don't get like zoologists. What's going on here? So all of America's carnivore biologists proceed to go and sort of like huddle there and decide they're going on strike. They are not going to give any more talks until people explain what's up. They like eat all the donuts that are left, go to the bar, start drinking, and they're going to refuse to have anything to do until these colonels explain what's actually going on. So the colonels obviously like need to get on the phone to Washington and call up and sort of get permission. They come back and say, okay, because you guys are all our best friends, we're going to tell you what's really going on. We're really not making Star Wars walkers. Here's what we're really doing. We're from the tank corps, and we've built this new tank recently, and it was what was called the Sherman tank. And apparently for all of history, what you do if you're in the tank corps is what you do is you just bash the hell out of everything and drive your tank to the highest spot around and just shoot anything that moves. But the Sherman tank apparently was like the greatest tank that had ever been built. It could drive like 60 miles an hour, and it could fire missiles when it was bouncing upside down out of ditches and gyroscopic this and that, and it was the greatest, most mobile tank. And they were having a problem, which was they would put in their tank cores in there, and what they would do was bash the hell out of everything and drive to the highest spot around and just shoot anything that moved. So the US Army Corps decided that they needed to teach their troops, their army, their tank corps, how to hunt like carnivores. And thus, here they invited all of America's carnivore biologists to come in and teach us how to teach our tank crews how to hunt like carnivores. How do you figure out who's going to cut corners on the prey? How do you communicate if you're out of sight with each other? What do your hyenas do? What do your wolves do? What do your coyotes do? So at that point, like all of America's carnivores biologists say, whoa, we are way in over our heads here. So like a third of them instantly like march out shouting about Ho Chi Minh or whatever, given the age group of most America's carnivore biologists. And the rest of them huddled there, and they come back and they said, well, these are very difficult questions to answer. So the military guys say, well, yes, we will give you money for your research. So at that point, all of America's carnivore biologists decide they're now best friends with these Army Corps guys. They go through the rest of the conference telling them all about the hunting techniques of their animals, and with careful instructions as to who to submit grants to. They all immediately go back to the universities, write grants. My friend writes this grant for like 4 Sherman tanks and night viewing goggles for like a Death Star and flamethrowers for his hyenas and all of that. All of America's carnivore biologists send in their grant proposals to this P.O. box at the Pentagon, and nobody has ever heard from any of these Army guys again. And this was about 15 years ago, and to this day, none of them know what were these people really trying to find out from us at this meeting. This was this totally bizarre incident showing that somebody or other in the tank corps is sitting around trying to figure out what is it that coyotes and marmots and hyenas do.
For more, please visit us at stanford.edu.